Did you know that YouTube's recommendation engine first used the decision trees algorithm before it became the monster AI that it is today? Decision trees are behind many things you use daily, from chatbots to medical diagnosis tools to even self-driving cars like Tesla. And it doesn't just stop there. They are also behind many big companies like Amazon, Google, Facebook, and Apple, which are using these for ad targeting and personal recommendations. Hello everyone and welcome back to my YouTube channel. I am Selina, and in this week's video we are going to discuss the intuition behind one of the more complex algorithms called decision trees. We will understand the intuition by asking more and more complex questions as we move forward in the video. We will start by solving a mathematical problem to understand the concept behind decision trees, and we will end the video with a Python implementation of decision trees in Colab. So let's jump right in. So in simple terms, a decision tree is a machine learning algorithm in which one complex question is divided into multiple simple questions, and you move forward using yes or no. That is the simplest definition of a decision tree. Let's say you're trying to decide whether to buy a smartphone or not, and you have a couple of factors in mind, like the price, the brand, the camera quality, and the battery life. So here's how it works. Step 1 will be the first question that you will be asking, and that is the price within your budget? If yes, then you will go further. If no, then you will stop. Step 2, is the brand a trusted one? If yes, then you will keep evaluating and you will move on. If no, you will stop right there. Step 3, is the battery life good? If yes, then you will again keep evaluating, but you'll be one step closer to your goal. And step 4, does it have a good camera quality so that you can record your YouTube videos too? If yes, then you will buy this one. Let us now understand the different components of a decision tree with this example. Let's break down the different components. The first component is the root node or the top node. The very first question at the top of the tree is the root node. In this case, the root node asks about age, which starts the decision-making process. The lines connecting the nodes over here, young, middle-aged, and senior, are called branches. The branches represent different possible answers or outcomes of a question. For example, from the age node, there are 3 branches: young, middle-aged, and senior. The decision nodes are the rectangular nodes here: student, credit rating, and age. These are nodes that ask a question and split into more branches. Examples are age, student, and credit rating. Based on the answers to these questions, the decision making continues. Finally, we have the leaf nodes: no, yes, yes, no, and yes. These are the final outcomes of the decision process when no more questions are asked. For example, after answering all the questions, you get yes or no as the final decision. Each path from the root node to a leaf node represents a decision-making process based on the answers to the questions at each decision node. Now that we have understood a simple definition of what decision trees are, let us understand their history and their origin. Decision trees originated in the field of statistics in the early 1960s and 1970s. Although earlier work was involved with a more outdated algorithm called AID or automatic interaction detection, it was only in 1979 that Ross Quinlan introduced the ID3 algorithm. This was the first major use of information theory to split data, marking the real birth of decision trees as we know of them today. Since then, the decision tree algorithms have evolved a lot, with advancement in technology and introduction of new algorithms like CART, C4.5, XGBoost, and random forests. So how do decision trees work? Well, the most crucial process in a decision tree is splitting, and this process begins at the root node. The algorithm evaluates the different features and finds out the best way to split the data based on a chosen criterion. The end goal is to make different subsets of data with as much purity as is possible regarding the target variable. Let us now understand the different terms involved in this definition step by step. Let us first understand what information gain is. So information gain measures the reduction in uncertainty that is achieved by partitioning the data based on a given feature. Now I know that this sounds a little bit complex, so we'll take up an example to understand this. Think of it this way. Imagine that you are trying to guess what type of fruit is there in a closed bag. Now it can be either apples or oranges. So before opening the bag, you don't know anything. So your uncertainty level is very high. But then you decide that you will ask a question, that is the fruit red? Now based on this question, if you get the answer yes, so your uncertainty level falls down quickly. Why? Because now you are sure that it has to be an apple. So you have gained a lot by asking this question. And once again, if the answer to that question is no, again you have gained a lot because you know that it is an orange. So in both the cases, your uncertainty level has gone down. So in conclusion, information gain is a measure of how much you learn by asking a question. The better the question, the more you learn. Our next important term is Gini impurity. So Gini impurity tells us how mixed up our data is. So it tells you how likely you are to get your guess wrong if you randomly guess the item from a group. Once again, let us understand this with the help of an example. Let's say you have a fruit bowl with apples and oranges. Now, if this bowl had all apples, then the Gini impurity value would be 0 because this would be completely pure. There are only apples in it and we want an apple. But let's say there are 5 apples and 5 oranges. Then this is completely mixed up and it is a maximum impurity case where the Gini value would be 0.5. Let us now understand the terms of target variable and purity in a subset. So what is a target variable? A target variable is what we are trying to predict or classify. So in the case of a car loan example, a target variable is either approved or not approved. Purity, on the other hand, refers to how homogeneous a subset is regarding the target variable. So in the case of a car loan, a subset is called pure if all of its elements are approved loans or they are all not approved loans. And it is an impure subset if it is a mixture of approved and non-approved loans. Let us now understand how the decision tree splits the data and forms pure groups for the target variable. We'll start with the credit score, which is the root node. Let us first look at how the data set is. So we have the applicant ID, the credit score, the income in dollars, the age, and whether the loan was approved or not, or maybe. So this is our target variable. In this we have 3 components: yes, no, and maybe. Now let us take a look at our decision tree and see what are the further steps. So first, based on the credit score, we divide or split our dataset into 2. One is if the credit score is greater than 700, and the next one is if it is lesser than or equal to 700. So this is group 1, where the credit score is greater than 700. And this is group 2, where the credit score is lesser than or equal to 700. We have 5 applicants in group 1 and 3 in group 2. Here, once we come back, we can look that if the credit score is greater than 700, we are further making a split based on another feature, that is income. So if it is greater than $50K, then it is approved, and if it is lesser than or equal to $50K, then our target variable is maybe. Let us look at this split even further. So subgroup 1A, that is income is greater than $50,000. Over here you can see the income is greater than $50,000. And subgroup 1B is if the income is lesser than or equal to $50,000. Next, we will split our group B. Let us see how we split. Group B is split based on age. So if the age is greater than 30, then maybe the loan is approved. And if it is lesser than or equal to 30, then it is definitely not approved. Here we can see that for age greater than 30, we have no applicants. But for age lesser than or equal to 30, that is subgroup 2B, we have 3 applicants. Hence, we have completely split our dataset using the decision tree algorithm. But decision trees don't stop there. things can get more tricky and complex when there are larger data sets and we ask more and more specific questions. So the answer gets tailored to the training data. And this problem is called overfitting. That is why we need to prune the tree, cutting away unnecessary branches that are causing the overfitting. This helps the model to generalize better and perform better on testing data. This can be done in two ways, either pre-pruning, that is done before the model is trained, or post-pruning, that is done after the model is trained. Random forest is another advancement in the decision tree technique, wherein we take multiple decision trees and their outcomes and find one single result. We will discuss this algorithm in the later videos. Let us now look at a Python implementation of decision trees using Colab and scikit-learn. So we start by installing the necessary library, that is scikit-learn, from which we will obtain the decision tree classifier. Next, we import the necessary libraries apart from scikit-learn, most importantly matplotlib.pyplot, to plot our decision tree. Next, we load our dataset. In our case, it is the iris dataset. It has the features like petal length, petal width, and sepal width. And the target variables are the labels or the flower species like setosa, virginica, and versicolor. We then split the dataset into training and testing using train test split. The test size is 0.3, which means that 30% of the total dataset is used for testing and 70% for training. Then we create a decision tree classifier object. Our variable is CLF, and we train the classifier by fitting the model and then predicting on the test set, that is X-test, which is part of the 30% of the dataset. Next, we evaluate the model's accuracy using metrics.accuracy score, which gives the accuracy score in terms of a percentage. Here we can see that the accuracy is completely correct. It is 100%. The final step is plotting the decision tree. This is done using PLT. And over here, as you can see, it has plotted the entire decision tree for us. The first root node that it took was the petal width. The criterion which we are using to split is the Gini index. Here you can see at the end, these are our target variables. We've got versicolor, 34 samples of it, virginica 1 sample, virginica again 3 samples, and it continues. So that's decision trees, a complex yet easy to understand algorithm which breaks down complex questions into easy step-by-step yes or no questions. Whether it is credit scoring or medical diagnosis, decision trees are everywhere making smart choices. If you found this video helpful, then don't forget to like, share, and subscribe. I'll be back next week with another intuition behind another machine learning algorithm. Till then, thank you for watching and happy Diwali.